Okay, so we look like we have some pretty good people here today. I hope we get more. So good morning to all of you. Let's go to, remember I said to you guys, I'm going to put in our online transition some examples here. And so I did just that. So we do have some examples that we want to go through. And I wanted you guys to look over this weekend. Hopefully you did. And this is on PDF format online. So I did some of this work. And I asked you guys to go over the probability multiple selections. If you guys remember. Let's get rid of that. I already have that there. Probability multiple selections. Let me take a look for it here. There we go. I wanted you guys to do the with replacement. Okay, and the with replacement, I believe, with the deck of cards here. So question 17 to 25. If you look here, you select 3 different cards. What's the probability there are? And there's 17 to 25, okay? Now, this is all with replacement, meaning you put the cards back. Okay, so we had 3 different. Let's go to that last page. There it is. Okay, so 26 to 34, I apologize. If you select 3 cards at random with replacement, what's the probability? They're all kings, all hearts, all red cards, and so on, right? So these are the kind of questions that I asked you guys to look over, and hopefully you guys did. And so I'm going to have to talk a few things about a couple of these definitions. This is why I'm bringing this up, because it's going to be an important detail for us. But if you look here, I did do these examples on our website. Did I? Oh, 25? None are less than 4. Okay. Well, then I will, and I'm going to remind you, let's kind of do some of those just for now to get started, because it's going to be what we want to base our lecture on. So I'll do that. I guess that's how I did it. I apologize. I guess that wasn't up. But let's take a look at question like this, like 26, right? Now, this is going to be where you select all kings. Remember that? That's the question for 26. This is going to be now with replacement. And I'm not going to do all of them, because by now you guys should be okay. And I know you can't see, so let's make it so that you can see. Okay? Okay. All kings. This is with replacement. And don't forget, we're going to select again 3 cards. So this is a good place to start. Okay, so I hope you guys have had a good weekend. I hope you've been working on your probability and statistics. Okay, selecting 3 cards with replacement. What's the chance they're all kings? Here we go. Let's write this multiplication rule down. That's the probability. If they're all kings, the first selected card is a king. Okay, and the second selected card is a king. And the third selected card is a king. Now, this is what this means again. That's the probability the first is a king, times the probability the second is a king, given that first card's a king, times the probability the third is a king, given the first is a king, and the second's a king. So I want to say to you guys again here, right? We're going to answer these questions, but this time it's going to be with replacement. So we're going to have 3 fractions. Okay? 3 fractions. So let's stop and think about this, right? If we select a card at random, what's the chance that it's a king? Well, there's 4 kings out of 52 cards. We know that one already, right? We've been seeing that for quite some time. All right. Now, let's go to the next question. If you select a second card here, right? And the second card is going to be a king. Remember the following here. This has happened. This is known. So the chance that the second card's a king, given that we selected a card first, we found that it was a king, that's known, that's happened, that first selection has happened. What do we do with that king? Did we throw it out the window? Or did we put it right back in the bag, or back in the shuffle to reshuffle again, back in the deck, right? What'd you do with that first card that you selected that was a king? Did you put it back, or did you leave it out? So question 6 and the rest of them from this point, what do we know? If you guys recall, this is again what? With replacement. Okay? So this here is going to be with replacement. So that means you're going to have to put this what? Back. You're putting the card back in the deck. So what's the chance that the second card's a king if you know the first selected card was a king and you put it back, right? Do you guys remember this? What do you do? Let's see what you guys think. Matt, let's see what Matt says. Right? Matt and Joanna. Matt says, guess what? It's 4 out of 52 again. Matt, if I had a bag of Flamin' Hots, right, you'd get that bag. So it's 4 out of 52. Good job. Absolutely. Okay, so that's the second selected card. Now, go over here and you say, okay, what's happened here? Well, we're going to have to deduce the probability that the third card is a king, given that the first is a king and the second's a king. And I want to make sure you guys understand this detail, right? This in gray has happened, and this represents the past. This is your what? Past, ladies and gentlemen. So, given the past, right, what's the probability the third card is a king, given that you know the first is a king and the second's a king? Remember, this is without replacement. Well, if it's, sorry, this is with replacement. This is with replacement. Let's say it 3 times. So with replacement, you put the card back in the deck. Because you put the card back in the deck, the first 2 cards that were kings, they're back in our deck. That means we still have 52 cards in the deck, and 4 of them are kings. So what you end up getting, if you guys already did this, look that over. Yes, this is going to equal 4 out of 52 to the third power, right? To the third power. So when we go to our calculator, we say, okay, calculator TI. All we have to ask the calculator to do now is say, all right, 4 divided by 52 raised to the third power. What do we get? Now, notice this. 4.55, 166, 1356, and then I get this e to the minus 4 power. Don't ignore the e to the minus 4 power, because if you guys remember, you cannot at all have a probability that's smaller than or bigger than 1, right? Probably a 4.55 does not exist. So if you guys remember, tell me what this means, right? Tell me exactly what this means. Anybody know? Right? What are we looking at? I know there's a delay. You guys should know what we're looking at because it's going to be an important detail. Okay. We have here Annabelle, right? Annabelle Castro. Look what she says she has. She has the answer 0.00. She has 3 zeros and then 455,166. Well, let's stop and think about this if you guys recall, right? And so is Jackie Lugo. She has the right answer, right? So what I want to remark here and say, and I'm going to write this down, what you're seeing here is scientific notation, right? This here, e to the minus 4 means move the decimal point, this particular decimal point right up here. Move that 4 spaces. Here we go. Move that 4 spaces to the left. 1, 2, 3, and 4. There's your new decimal. So that's 0, 0, and 0. And yeah, this e to the minus 4 is really 10 to the minus 4. In all honesty, I would rather them write down that 10 to the minus 4, but okay. So again, we're going to approximate today to the nearest 10 thousandths again because these are kind of some small numbers, right? So if I ask you tenths, 100,000, 10,000, look at the digit to the right. What do I do with the 4? Do I change it to a 5 or do I leave it alone? We change it to a what? 5. And ladies and gentlemen, the answer is approximately 0.0005. And this as a percent, so that you guys know, is actually 0.05%. So I want to also say that this event is very much not likely. Remember, anything that's less than 5% is not likely. And this probability is very small. So it's not likely you're going to select 3 kings with replacement. Now, this is a pretty big deal. Okay? This is a very, very big deal because we're transitioning here. So as you guys can see, with replacement really means the following. Our past does not matter. I'm going to say this again. The past simply does not matter when it's with replacement. Everything starts all over again. And that's an extremely important idea. Okay? The past doesn't matter. So if I go to question number 27, let's remember, these are with replacement. And what we just know and we discovered here is the past doesn't matter, right? Here we go. Let's look at what this question would be, number 27 here. And yes, did we do the 10th? I'm sorry, did I do 10,000s? What did I say? 10th, 100,000? Yes, we did 10,000s. So that's approximated to the 10,000s. Okay? Okay, good job. Let's go to the next kind of question here. So I think I have it here. Probability, multiple selections. Let me leave it up here. All right. And let's go to the last page, page 5. I want you guys to note 27. All hearts. With replacement. Okay. And we're selecting 3 again. So remember that. We're doing that one at a time. So let me write down this meaning here. This is the probability. The first is a heart. The second's a heart. And the third's a heart. multiplication rule says this. That's a probability the first is a heart times a chance the second's a heart, given that first is a heart, times a chance the third is a heart, given the first is a heart, and your second is a heart. So let's reach in the bag, pull out a card, I reach in the deck. What's the chance of selecting a heart? Well, you say there's 13 hearts out of 52 cards. Also, now, let's go to the next probability. What's happened and what is known is that in the past, you selected a heart. Now, remember, like the last example, when this is going to be with replacement, your past doesn't matter. You start all over again because I said it again, when this is with replacement, your past doesn't matter. With replacement, you put the card back in the deck and your past does not matter. So the chance that you select a second card and it being a heart, again, is going to be 13 out of what? 52. Because your past doesn't matter. You put the card back in the deck. The next probability, what we know in the past, is that the first card that was selected was a heart, and the second card that was selected was a heart. Remember, since your past doesn't matter, you put those cards back in the deck because this is with replacement, right? With replacement. So the chance that the third card again is a heart, because it starts all over again, your past doesn't matter, is 13 out of 52. And you notice this will give you 13 out of 52, again, to the third power. And some of you guys might say, but Mr. Judge, isn't that also the same as 1/4 to the third power? It is, because 13 out of 52 does reduce to the third power. But since you guys are using your TI calculator here, right? Here's what you get. Let's clear that. We can put 13 out of 52 and raise that to the third power. Okay, and we know what that equals. Or we can raise 1 divided by 4, and then we raise that to the third power. And what do you get? So notice, you get the same thing, right? So notice this is not in scientific notation anymore, right? We got 0, 1, 5, 6, 2, 5. Let's go to this. Let's go to the 10,000s again. Tens, 100, 1,000. The 6 is in the 10,000s position, and we're looking at the 2. What does that mean I do? I keep the 6 as it is. And is this in the 10,000s position? Tens, 100,000, 10,000. That's right. Here's our answer. But I want to kind of make something very clear here with this idea. When you put things back with replacement, that really means the past doesn't matter. Now, these are some good examples. I'll probably finish them off with another update with examples in this. But I want to also remark here for you guys. The last part of this is 2 very important definitions, because this is what I'm getting at. We have the definition here that we say 2 events are independent, right? And I say A and B are independent. These 2 events are independent if the probability of A does not equal the probability of A given B. This is what it means to be independent. It means the condition B does not change the likelihood of A. B has no effect on A. Now, let me write this down here for us. Okay, because I want to use this here for you. The probability of A being equal to the probability of A given some condition. And remember, this is equal. I want to point out some detail. Here's B. This is known. This is in the past. This has happened. And when you have equality, and I'm going to paint this red here, this is very special. This means here that A and B are independent of one another. It's a very important, powerful idea. To show you the meaning of this definition of being independent, and I want to remark, I'm going to use it in a different context. So I'm going to say to you guys the following here. You know, there's a chance that you get struck by lightning. I hope you don't, but there's a chance. Okay? So let that be your A, being struck by lightning. This is A right here. Okay? So I don't know what it is. It's something like 1 in 750,000 people, I guess. I don't know. I thought I remember that statistic. I could be wrong. But that's the chance you get struck by lightning. Now, is this equal to? Here's what I want to remark. Let me actually say to you guys, let's actually look at a condition now. Given that you wear green shoes. Okay? So what's known, what is happening is you got on some green shoes. So let's say this to you. What's the chance that you get struck by lightning? Right? And what's known? You got some green shoes. You got green shoes now. What's the chance you get struck by lightning? Here's how we have to think about this. Does the chance here, or does the fact that you're wearing green shoes change the likelihood of you being struck by lightning? Does it change that likelihood? Yes or no? What do you guys think? Wearing green shoes. Are you more likely to be struck by lightning, or less likely, or just simply the same? Does the fact that you have green shoes even matter? What do you guys think? Give you guys a few seconds to think about that. I'm thinking I need some thinking music here to play for you guys, right? Thank you, Cassandra. Thank you, Michael Salazar. Yeah, thank you, Annabelle. So, yes, here's my point. Ladies and gentlemen, this is a very important thing to know. The fact that you're wearing green shoes does not change the chance that you get struck by lightning. What we're saying is that the two events, being struck by lightning and wearing green shoes, are independent of one another. This is a classic example that I use. Okay? Now, if it does change your probability, right? Let me write this down so you guys know. Probability of A. It's the probability of A given B. If it does change, and I'm going to write down change this way for you guys. If it's not the same, meaning if it's greater or if it's less than in terms of likelihood. This here, we say A and B are dependent events. These are independent events. So this is the definitions that we're talking about. This is what it means to be dependent. Now, what I do typically here is My favorite example is the following: being struck by lightning. The chance of being struck by lightning, is that the same? Let's introduce some condition to you. Let's see what you guys say now. Let's introduce this condition. Chance of being struck by lightning, given that now you fly a kite in a thunderstorm with a metal key attached atop the highest hill. Here's what's going on. Here's what's happening. All of this is happening, ladies and gentlemen. You're flying a kite now in a thunderstorm with a metal key attached atop the highest hill. Does that change the chance of being struck by lightning? Does that increase it? Does that decrease it? The second that changes, the second this new introduced criteria that's known that's happened, does that increase your probability or does that decrease your probability? What do you guys think? What should that be? Should it be greater than or less than? And again, I'm going to put some, I'm going to find some thinking, noise. No, that's not it. There we go. Let's think. What do you guys think? Do you want to go out there and fly a kite in a thunderstorm with a metal key attached to the top of a hill? What do you guys think? Do you want to do that? I would say that's not a very good idea. And we got Jessica Ortiz, Jessica Ortiz. Good job, Jessica. Jessica Ortiz, she's saying, you know what? It's going to increase your chance. Good, Jessica. That's some common sense, okay? Thank you. You got common sense. What that means is don't go fly a kite in a thunderstorm atop the highest hill with a metal key attached, because that you just changed the chance of being struck by lightning. You increased it. Now, increasing is simply the same as saying not equal here. And when they're not equal, these events are known as being independent or dependent. I'm sorry. I'm choking here. These are known as dependent events, okay? Dependent. So all you guys have some good common sense. All right. In other words, you're changing your likelihood. So this is how I describe to people dependent events and independent events. So let's go back. Here's my point. Remember these questions here, like 27 and 26 with replacement? With replacement, notice what's going on here. These conditions that we just talked about, these things that are known, these things that are happened. What do you guys think? What's the deal here? These things that are known, these things that are happened have no effect on the chance of the present. So probably the second card's a heart. We already said it's 3 out of 15. That's the same. The past had no effect. What that means is that's the same as the probability that the second card was a heart, right? Put it here. Doesn't matter what the condition was, it had no effect. Similarly, the next probability that the third card was a heart, the condition of the first two being hearts, because this is with replacement, had no effect. These probabilities are the same. So what would you guys associate? What's analogous? Stop and think of the definitions we just talked about. Being independent and being dependent. When you're working with replacement, what is that analogous to? Events being dependent or independent? What would you guys say? Sorry, wrong one. Nope. Well, that might be it. We're hearing crickets, right? All right, you guys, settle down. It wasn't that funny. I know. With replacement, what is that analogous to? Independence or dependence? Okay. Okay, Joanna. B does not affect A. Thank you, Joanna. You are right. And since B has no effect, this is analogous to being what? Pendant. Independent events. There we go. You guys are completely right. Thank you. Thank you, Cindy. Thank you, Raphael. Thank you, Jackie. Yes. That's important for us. We're going to see this. They're independent. So you're right. Let's look at question now, number 28, and see if we can put a little bit more of this together. You guys are completely right. So for 28, let's go down here. Okay. 28. We're going to try this one. I'm going to change my notation on you guys so you guys know what I'm talking about. 28, they're going to want to know here. Try to find that page. All red cards. Chances are all red. That's the probability the first is red. And the second's red. And the third is red. So let's write this detail here. Probability the first is red times the probability the second's red, given the first is red, times the probability the third is red, given the first is red, and second's red. Okay, so you guys know. Remember, this is with replacement. Okay? With replacement. This is analogous, and we're selecting 3. This is analogous to being again independent. So this is what it means. The chance your first selected card is red times the chance the second is red times the chance the third is red, because these events in the past have no effect on the present. The past has no effect on the present. That is why I can say to you guys, the probability the second is red is the same as the probability the second is red. I don't care about the past. This does not matter. This does not matter. Your past. Probably the third is red given the past. Who cares? Our past doesn't matter, because these events, again, are what? Independent. Go back to that definition. Independent means the probability over here is equal. Okay? This is what we're using. Those are equal. All right. So we can say, answer the first question. What's the chance that that card you select, that first card, is red? You can say, oh, well, Mr. Judge, half those cards are red. So that's 1 out of 2. Okay. Well, what's the chance the second's red? Well, the pass doesn't matter. That's also 1 out of 2. What's the chance the third is red? 1 out of 2. That's 1 out of 2 to the third power. So being independent simply means we just repeat that probability because the pass doesn't matter. They're independent. And that's what happens with replacement. Pass doesn't matter. They're independent. So when I go to the calculator and I say, let's compute this, we want 1 out of 2 raised to the third power. Now, we can say, let's go out to the 10,000ths. It won't matter what we say, what we go out to, because your answer is automatically written here for you guys, right? The answer is automatically 0.125. So when we put our box here, we're done. We can say 10,000ths, but we could put zeros there. We don't need to, but this answer is 0.125. And as a percent, this is 12.5%. So ladies and gentlemen, you could go about all of this with replacement business, knowing simply that you just keep putting and repeating the probabilities, because the past here doesn't even matter. Okay, you start all over again with your selected cards because you keep putting those cards back in the deck as you select them. So this is an important detail about being independent and being dependent. And I just want to give you guys a note. Let's note. Remember the without replacement. And let me write it down in words. Without replacement, what do you think that's analogous to? If the probability changes, remember, with replacement, it starts all over again because you put the items back in. Without replacement means you throw it out the window. So what do you think that's analogous to? I'll give you a hint. It's either dependent events or independent events. If we know with replacement is independent events, what do you think without replacement would be? Take a good guess. Anybody? These are dependent events. Okay, Cindy has it right. They're dependent. All right, James Ho has it right. They're what? Dependent. Jackie Lugo has it right. They are dependent. Absolutely. Good job, you guys. So that's kind of the lesson today, is on independence and dependence. Let me finish a couple of things here for you guys. Let's see, number 29 here. So just kind of look at that quick question here. See how fast we can kind of do some of these, right? all face cards. Okay, all face cards. Remember, we're selecting 3. This is without replacement. I'm sorry, this is with replacement. Boy, I really like that. So when you have with replacement, remember, this is analogous to independent events. So with all 3, here's what we can say. Probability. The first is a face card. And the second is a face card. And the third is a face card. I could now write this very simply without the conditional part, because I know that they're equal. I don't have to write the conditional part anymore. And that's a good, or I should say that's an advantage. We don't write the conditional part because it's equal. These events are, again, independent. That's why we could put this, that's why I could leave the conditional part out. So let's stop and think about, what does it mean to have a face card? It's a card with a face. So how many cards have a face? I might have to go all the way back up here to look at them. Here we go. We got the three looks like spades, 3 clubs, 3 spades, 3 hearts, 3 diamonds, 3, 3, 3, 3. 3 times 4, is that what? 12 out of 52. The next one, 12 out of 52. 12 out of 52. Right? We okay with that? Cards with faces. And then you say to me, can I just write this as 12 out of 52 to the 3rd power? The answer is yes. Our TI comes into play. And we can say now 12 divided by 52 raised to the what? 3rd power. So let's write these numbers down. 0.012289894857. If we go into the 10,000s again, we say tens, 100,000, 10,000. We put our eyeball on the 8. Is that right? Take a look. So what is that eyeball? Let's see. Tens, 100,000, 10,000s. What does that eyeball say to do? What do I do with the 8? Do I add 1 to it and make it a 9? I'm sorry, what do I do with the 2? I apologize. What do I do with the 2? Do I add 1 to it and make it a 3, or do I leave it alone? Since I'm looking at the digit to the right, which is an 8, I add 1 to 2, we get a 3. It's about 1.2%, so you guys know. Let's actually be very, very accurate. Let's use this data. This is 1.223%. So that means that this event is not likely. So it's not likely you're going to actually select 3 face cards with replacement. And here's your final answer. Did I make a mistake on this? Tens, 100,000, right? It's 0.01. 0.01. Yes, I did. Oh, weird. 0.01 what? 23. Let's change that. Good. 0.0123. Okay. We got Jessica Ortiz correcting us there. Good. 0.0123. 0123. That's kind of interesting. Yeah. 0123. I don't know if you guys get it, but okay. 0123. Sorry, you guys. Okay, here's an example of why we care about this concept of being independent and dependent. Now, I'm going to change this example on you guys. I'm going to write something down here for you guys. Let's change the subject because this is similar to questions on my website and even questions in your book. Let's say, for example, you got to wake up for class. And you have to buy, or I should say, you can't be late. You're going to wake up for class. You buy 2 alarm clocks. So you're going to buy 2 alarm clocks that function. Here's the word. Independently from one another. So you buy 2 alarm clocks. Here's what you know. The chance an alarm clock functions is 98% of the time. What's the probability both clocks and I'm going to write it here, do not function? Okay? And let me get rid of our notes there. This is a classic kind of question. Okay, very, very classic because you have 2 alarm clocks now. Sorry, here's my 2 clocks. You never guess my parents are artists, right? 2 clocks, there they are. We're going to say that these clocks function here. Here's the key phrase. Independently from one another. You know, maybe you have them on different circuits in the house type of thing, right? You want them to be independent of one another. It's an important detail. They want to know, what's the chance that both of these clocks do not function? Because remember, you have to wake up in the morning, you have to come to class, and if both fail, right, both of them fail, then they are not waking you up. You need at least one to work. Okay, so we want to know, what's the probability both clocks do not function? Let's write this down in words. Probability. The first does not what? Function. And the second does not function. Because they said, what's the chance that what? Both clocks do not function, meaning they didn't work. Okay, you do want redundancy in alarm clocks. This here is no longer thinking of marbles or cards. This is real world now, ladies and gentlemen. This is a redundant system. See, you buy 2 clocks so that you can actually ensure yourself from waking up. Hey, you need to wake up, get 3 clocks. Oh, get 4, get 5, whatever. This is the exercise in being independent and dependent. This is why it's important. So here we go. This equals the probability the first does not function times the probability the second does not function given the first does not function. Or even better, the probability the first does not function, times the probability the second does not function. Does anybody know why did I get rid of the condition? Why don't I care at all about this? Because these events again are, here's a key phrase, independent. They're independent. So this chance is simply probability of not functioning. We're almost finishing the question here. So I want to just remark about that. These are independent. So who can ask me now, what's the chance that the first clock does not function? Chance, first clock does not function. What's that chance? For some Flamin' Hots. Oops. Sorry. Flamin' Hots. How do we find the probability the first clock does not function? Anybody want to tell me? Well, I got an answer over here. Joanna is saying 2%. Okay? She's saying 2%. Now, what I understand that means, 2% as a decimal is 0.02. Is that right? Now, let's be careful. This is not 50%. It's not 1/2. So I'm gonna tell you guys, 50%, 1/2 is very wrong. Okay? It's wrong. It's going to be 2 out of 100. You say, how is that 2 out of 100? Let's go back over here. Remember, what does this phrase mean for you? The chance that an alarm clock functions, that's working, is 98% of the time. So what that means here is the chance that it functions, probability, and I'll say function, for any clock is 0.98. This is as a probability. Okay? This is an important detail. So the chance a clock works is 0.98 because it's 98% of the time. Okay? So just because a clock can function or not function, don't say 1/2. Don't say 50%. Now, you're going to use the complement rule. Remember what the complement rule is. Okay? Probability, it does not function, is 1 minus the probability of functioning. And let's get rid of this. Okay? Well, this is going to be 1 minus 0.98. And let me go back. One minus 0.98. And what's 1 minus 0.98? 0.02. 2% of the time, both clocks do not function in this model. 98% of the time they function, 2% of the time they do not, right? 98 out of 100 they function, 2 out of 100 they do not. You're using the complement rule. So you're going to put this number down here, 0.02. Good. Now, what's the other number? Because 2%, yes, Joanna, is 0.02. So flaming hot's for you. Okay? What about the next probability? What about the next clock? Because they function independently, what's that probability going to be? Also what? 0.02. So you can say, or you could write this down as 0.02 now to the second power. Okay? So this is how we answer these questions here. So when I go to my TI now, here's a TI. I want to say to the TI now, okay, TI, what is 0.02 raised to my second power? And notice what I get. I get this again. 4e to the minus 4 power. And you guys know, what is e to the minus 4 really again? Well, this is scientific notation. 10 to the minus 4. Scientific notation, 10 to the minus 4. So 4 times 10 to the minus 4. Remember, here's my 4, right? I got 4. Where's the decimal with the whole number? It's behind the number, right? And then you move this here to what? 1, 2, 3, and 4. You're going to plug in your zeros. Here's what you get. 1, 2, 3, 4. So, ladies and gentlemen, the chance that both functions, let's see what we just did. This is the chance that both clocks, right, do not function. Both clocks do not function. Notice, this is a very small probability. So we have Annabelle Castro getting the answer right. We got Joanna Landeros getting the answer right here. This is a very small chance. This is not likely. It's not likely 2 alarm clocks do not function. This is why you buy 2. Okay? This is the reason 2 clocks are being purchased, because it's not likely that both will not function. Because you need at least one clock to function so that you can wake up, right? Okay, you guys okay with that? This is pretty good. This is pretty good. Now, I want you guys to think about this one here. Here's a note. What's the benefit? If we do this problem right again here, let's note. What about buying 3 clocks? You're going to buy 3 clocks now. You go buy 3 clocks. Is there any benefit to purchasing 3 clocks, again, that operate, here's the key word, independently of one another? 3 clocks. The question again is, what's the probability? Here's my question. Let's write that down. What's the probability now? All do not function. That's the first. Does not function. And the what? Second. Does not function. And the third. Does not function. Well, because they're independent. first does not function times the probability the second does not function times the probability the third does not function. Okay, as you guys seen before, the chance the first clock does not function is 0.02. The chance the second clock does not function is 0.02. The chance the third clock does not function is 0.02, because they all operate, once again, independently. They're independent of one another. So in our calculator, we can use mathematics. We can say the following. This is equal to 0.02 to the third power. We want to go to the calculator. KTI, here's what we get. 0.02 raised now to the third power. And then we end up with this 8 again. We got the 8 now, e to the minus 6 power. What that means, again, e to the minus 6, we put the whole number, the decimal behind the 8, and we're going to have to move this decimal point. 1, 2, 3, 4, 5, 6. You move it 6 spaces to the left. What that means is with every blank, you put a 0. So if I had to move it 6 spaces and fill in the blanks, I got 1, 2, 3, 4, 5, and I got an 8. Here is your final answer. So let's see. I think we have who? Annabelle. We have Joanna Linderos. Okay. If you can see that, and I'm not sure I can, it looks like there's 5 zeros. Are there 5 zeros? Right? Let's see. 1, 2, 3, 4, 5. 1, 2, 3, 4. Yeah, 5 zeros and an 8. Ladies and gentlemen, this is your final answer. So this is every gory detail that we put in here to get these answers here. So as you can see, being independent is a very, very powerful kind of thing. Okay? It's very powerful. Let me check a few things here. Okay. All right, being independent. So we could do this all day long, ladies and gentlemen. This is 3 calculators. You can buy 4 calculators. Alarm clocks. You can buy 3 alarm clocks. You could buy 4 alarm clocks. You could buy 5 alarm clocks. How about if we do this? Let's do another note. Same example. Let's do 5 alarm clocks. Can you guys generalize now? If I say 5 alarm clocks, here's what you do. It's going to be what? 0.02 to the 5th power. Right? Here's what you want to pay attention to. 5 clocks, 0.02 to the 5th power. Just like the last example. 3 clocks, 0.02. 0.02 to that 3rd power. So if you keep buying clocks, they all function again. The key phrase here today, independent. independent of one another. The past has no effect on the present, analogous to being with replacement. We can just actually use this for any number of clocks now. So go to the TI, 0.02 to the fifth power now. If we go there, we can say, okay, 0.02 raised to the fifth power. And in this example, the calculator says, here we go, we get 3.2 e to the minus 9 power. Right? So, what do we do now? We simply move what? We move the decimal. Here's 3.2. We move it 9 spaces to the left. I'm going to have to put that 3.2 way over here. 1, 2, 3, 4, 5, 6, 7, 8, and 9. So I got 1, 2, 3, 4, 5, 6, 7, 8 zeros. 8 zeros there. 0.1, 2, 3, 4, 5, 6, 7, 8, followed by a 3, 2. And let's put a nice box here today. Yeah, so as you guys can see, it is better for you to buy more than one alarm clock. This is the chance now that what happens here. This is the chance all 5 do not function. That's the worst case scenario, right? All 5 not working. Well, guess what? It's not likely that all 5 will not work because this event is pretty close to 0. Not what? Not likely. Very, very close to 0. Okay? Not likely. Yeah. That's why you buy 5 alarm clocks and make sure they function independently. Put them on different circuits in the house. Or maybe on a couple of circuits, batteries, whatever you want. They're all different clocks with batteries. Okay, they're all functioning independent of one another. And that's why you care about independence. Okay, if one fails, it doesn't affect the others, right? It's kind of like Christmas tree lights. In the old days, you used to have these. The new days, you have parallel Christmas tree lights. In the old days, you had series, which is bad. We'll talk more about that. But nevertheless, this is where we're at with this multiple selection. So I gave you guys a very comprehensive review here of multiple selections and conditional probability. We're going to move forward with some of these things. But before I do, I sent you guys a survey over the weekend, and I hope you guys filled that out, right? Fill out that survey because we have to start thinking about how we're going to do our tests, how all that's going to happen. So I'm not sure if it was this class or another class. Let me go back to all the questions here. We're going to start answering some very good questions. I did get a question. Okay. I have a question by somebody that says, will the test be multiple choice or open answers? The tests are never multiple choice. Okay, I'm gonna look at your work. You're gonna have to compute the answer. They're not multiple choice. Okay, and also my computer does not have a camera. Will Proctorio still work? Okay, so let's go here. We got a question here, right? Got a very good question from Yvette. What I want to start off by saying to you guys is this. We're going to talk more about this Proctorio. Proctorio has some requirements. You need to have a computer or laptop with a camera. Also, you need to be running Chrome on it. Okay? Now, hold on for a second before you guys have a heart attack and say, oh my God, I'm in a bad spot. Well, you might be. Most of the responses that I got, people said yes, they have a computer with a laptop and internet access, and you have also a camera. Okay, good. Most people are like that. I did get some responses that have said things like, Mr. Judge, I'm watching this on my phone. I don't have a computer, laptop, internet access. Well, we're going to see how we handle that. What I want to say to you guys, though, is there's various things I can do, and I'm thinking about it. But I'm going to ask those of you guys that are just using your phones, maybe you have a brother or a sister who has a computer with internet access and can use Chrome and has a webcam or something or a camera on it. Maybe your father, maybe your mother, who knows? Maybe there's somebody in the household that has one. So I want to say, first of all, try to see if there's someone there. If there isn't, let me know. So those of you guys that don't have the tools there to do it this way, let me know, meaning you don't have a camera, because Proctorio won't work without a camera. So just let me know about that. Also, another important thing that we're going to need to have is an ability to scan. Okay, hopefully you guys, so you want to show your work, remember, so hopefully you guys can scan and show your work. And that's helpful. You have apps on your phones. If you're only using a phone, there are some apps out there that you can scan and you can show your work that way. That would be a good thing to do. So you guys know more about those applications than I do. Or maybe you have a scanner at home. If you have a scanner at home, you're good. But I'm not sure exactly what you guys have at home. Let me know, though. Don't be saying, well, I'm going to drop the class because I don't have a scanner. Oh, I don't have a laptop. Oh, my God. No, just, let me know. We could talk about it. We can all figure something out, okay? So we do want to figure things out here. This is an extraordinary time with extraordinary circumstances. We have to have extraordinary whatever to deal with it, right? So just think about that and do the work I gave you guys. So I gave you guys some web work. I gave you guys some book work. You should now be able to answer a lot of those questions in the web work and the book work. I mean, in fact, I'm even thinking about in the book work. If you look at questions in even 4.2 had multiple selections. And that goes all the way down to about 27, I believe. I must have given you guys the odds, like 9 to 27 odd in 4.2. That's something that you guys want to go back and look at, multiple selections. But I've completed the independence, the conditional probability, and multiple selection portion. And I just want you guys to know, stop to think about how we're going to take those tests. Yes, Proctorio is on our radar. But you do need some tools, and if you don't have them, let me know, okay? That's what you guys want to do. Now, I have office hours. In office hours, you go to Canvas. So make sure you guys are in Canvas here for my office hours, all right? And then we could talk about some of these issues in case you guys have some of those issues. So Canvas is also going to be the way we go do our test as well, so you guys know. It's going to be put in Canvas. So make sure you become familiar with that, with Canvas. And if you have to go to office hours, go to office hours. That's what they're for. So I'm going to be there like I'm always there. So anybody have any questions at this point? I hope I answered some of your questions. I got about 24 people. Anybody have any questions? I know it's going to give you guys, I know there's somewhat of a delay here, which is why you guys don't answer automatically. Oh. Already an applause. Okay, sorry. So let's wait for your questions because we do have a few minutes. Any questions? Are we good? All right, let's see. Any questions there? Oh, thank you. I want to say it was study guide. Oh, a study guide. Okay, we do have some questions. Good. Sorry about that. Okay. All right, Annabelle, I understand your situation. We're going to try to accommodate you, okay? Michael, I do have a laptop that I can use. Problem is that it's from my little sister's school and it doesn't work to install and runs Firefox only. Oh, okay. So here we go. All right, you guys, let's put this in. Okay, let's put some of these questions. Okay, Annabelle, we're going to try to accommodate you. If you want to go to my office hours, we're going to talk a little bit about that, okay? I'll let everybody else know this week. Michael says, I do have a laptop that it's my little sister's school and it doesn't install things. Yeah, I know that happens. Definitely, I get it, you know. A study guide. Erica, yeah, we can put some sort of form of study guide for you there. Absolutely. Cassandra, thank you so much. Cassandra, and 4.2, I'm kind of not, let me get this out. Cassandra's saying 4.2 homework. Let me look at the book. All right, Cassandra, let me do this. Yes, Cassandra, the answer to Cassandra's question, do we need to do 4.2, 5 to 29 odd? Yes, from the book. And your book, this book is kind of, they changed things on it, you know. They changed it backwards. So multiple selections, so you guys know, is actually in 4.2, and they gave you homework in 4.3. So you do want to do 5 to 29 odd, and that's from the book. And that's your homework. So some of you guys are going, hey, what's my homework, right? Here's James. All right, James, how do we turn in your homework? Well, we're going to probably have to do some scanning on that. So we're going to see about that. But make sure you do these things. Wait until, what was the past homework? All right, Michael, you have 4.2 now, 4.3, and you have your statistics lecture homework, the web work, right? So you have those kinds of things. So yes, Annabelle, right? You're going to have that homework from the web and the book. So keep track of that. You have both of them. Okay. So I answered some of these questions here. Yeah, James, we're going to have to figure that one out too. It's, you know, take a look and see if you guys on your smartphone, there is some ability to scan. Okay. So make sure you do some of that. Okay. Look into that. So you'd like to turn in your work. We're going to put this in Canvas. You want to use your phone and convert that via scanner. There's a scan app. Do those kinds of things. And if there's some issues, let me know and we'll talk about it. So every day here this week, we're going to talk a little bit about these things. Okay, so we have a lot of good questions for you guys. I hope I was able to answer some of them. But we're going to have to deal with those who don't have that technology portion. I'm going to have to figure a good part of this out. I'm not certain at the moment, but work on your book work. Work on your web work. Just keep those things in mind. And, let's communicate to each other. Go to office hours if you have to. Email me if you have to. And hopefully everything's going to work out for us. But, yeah, we're going to have to accommodate people. Let you guys know. So thank you, guys. You have some great questions today. I hope you guys learned something. And if I don't see you in office hours, I'll see you guys tomorrow. Take care. Stay safe.